m1 is f minus f1 plus t equal m1a. And in the vertical direction also equilibrium is as before, n minus m1g equals 0. That becomes your equation of motion. I would consider this T1 because there is two. Now, if I go from this point to the other point, that means I consider this portion of the system as a this portion of the system as the system. Then for this, your T from this rope, from this part, is transferred to this point. So T here is the opposite side. It's just as long as this rope, when the object 1 moves this way, this rope pull it that way, then in this point it will pull M2 in this direction. So it becomes the same force, but instead of being resistance force, is a driving force. So in that case, you have F2, you have F3. So in this case, T1 minus F2 plus F3 is M2 plus M3 times A. And then you can also change this, consider consider the last object as your system. So it becomes another situation where here is M1 and F, then you have T1, and then here T1 acting on M2. But then here is T2 pulling M3, and here is T2 resisting for M2. So if I consider, for example, this as my system, then the forcing acting on this M3 is T2 minus F3 is M3A. You can see A for all the objects because they're all moving the same, acceleration is the same, but it depends where we consider the system, the condition may change. And the rope between this object is just considered as an external force. If you consider the system just part of the system, the rope becomes external force acting on the system. But in this case, the rope is inside the system, so it doesn't count in the second law for equation of motion. But then here I didn't write it, but basically in this case, the vertical force, they balance each other. And we can also have this example in an inclined plane. So some of the example comes, for example, you have, let's say, inclined plane. In this situation, I consider like several cases. Theta, this is the mass that you have, MA, and then you have another mass, MB, and then let's say you have a force on B in this direction, just in a general case. And we know the mass normally projecting in perpendicular to the direction of motion. So MAG cosine theta, and parallel to the direction of motion, MAG sine theta. The same for B. So MBG cosine theta, and here I consider this one. This is MBG sine theta. So this one is for B, this one is for A, and you have also F. Now if I assume the whole part, that means both of the objects as a system, So the external force in acting on this system is also one frictional force. I assume the object goes upward, so the frictional force would be downward like this. F here the frictional force. So I hope we can see it, but in this case F is the driving force, this F is the resistive force, which is opposite, but also the part of mass opposing the motion, which is MAG sine theta for a mass of A plus MAG sine theta, MBG sine theta, the mass of the other one, equal to MA plus MB A. This is when you consider the whole thing as a system, but for the same example, and I have A, and then B, and this is F. Now I consider B as the system. So you do have the mass projecting in this direction, which is MBG sine theta, and MBG cosine theta for the mass of B projecting to the direction normal, to the direction of motion, and normal to the direction of motion. I assume you know this. But also between A and B there is a frictional force, which is F A to B. The frictional force acting from the surface of A to B. So B wants to go up, then this friction is brought down. So for that case, F minus F A to B plus MBG sine theta is MBA. That's when the object B is the mass. And you could basically, in the vertical direction, say N A to B, N A to B minus MBG cosine theta equals 0. Here I assume we know some of the things, like F is mu n, and therefore F A to B is mu A to B. So since this is equal to this, you can say that is mu and BG cosine theta. I just put this one inside the N, and I can calculate the F, and then if I put it here, you can measure, for example, F. But that becomes a bit more mathematical calculation. But we want to understand how to draw this free diagram and how to distinguish between different forces according to the considering which one is the system. So now I want to go and consider A as the system. So let's draw this here. I assume if you look and compare to the previous examples, you probably already know the answer. This becomes MA G sine theta and MAG cosine theta. I just assume the MA projected the mass to these two directions. Now, if this is F and I consider A as the system, then F is not the force acting on A. but the frictional force which B act on A, pulling A towards upward. So that becomes F B to A. That becomes your driving force. And then the frictional force here is F. And then you have N. And then you have BG cosine theta, the part of the mass of the B acting on A, pushing down. So the equation of motion becomes F B to A minus MAG sine theta plus F here, this force is MA. And in the vertical direction, N minus MBG cosine theta plus MAG cosine theta is equal to 0. Now we know that this F here is mu n, and n you can say from the first example or from here is equal to the adding of this, so it's mu mbg cosine theta. I would say mb cosine theta plus mag cosine theta, and we can substitute here, for example, instead of, but FBA to A is a force acting between here, so it's just proportional to the normal force at the surface between the two objects. So this is mu n A to B, and we know that n A to B is the same as we had it here. Is sorry, mu B to A, mu B to A, and mu N to B, and A to B, and N B to B, B to A, but they are all both the same, as equal to MBG cosine theta. So this becomes mu G, mu MBG cosine theta. That is the frictional force for the between the objects, and this is the frictional force for the considering both objects on top of each other. So you could see, even in case of inclined plane, we just have a cosine and sine. The mass is not completely perpendicular to the surface. The mass is this way, so we normally project the mass in two directions, and then the analysis of the system would become the same. You can have the same situation when you have a rope between the two objects and sitting on an inclined plane. And let's say, for example, you have an inclined plane like this, and then this is object A connected to object B, and then the force, for example, F acting here on object B, or you could also have object C here, just different. It doesn't really matter, but so in this case, if I consider the whole thing as a system, then you do have the forces of mass of B, which is MBG cosine theta and MBG sine theta, MCG cosine theta, MCG sine theta, and then for A, MAG cosine theta and MAG sine theta. And since we are considering the whole system as the whole mass as a system, the rope, the internal force, considered not affecting the equation motion. So you do have like the equation F minus the frictional force here is, if we say we're going up, is F B, and this one is F A. So F minus F A plus F B plus M A G sine theta plus M A M B G sine theta plus mcg sine theta equal to m1 plus m2 ma plus mb plus mc times a. That becomes the general equation of motion. And then for a, you do have na. So na is m minus mag cosine theta equals 0. And then in this case, there is NB. So this is NA, NB minus MBG cosine theta plus MCG cosine theta equals 0. This is in a vertical direction for this. This is vertical direction for this one. But now, if I consider, let's say, A as my system. So I have the same example. This is A, and this is B, this one is C, then this one is my force. Now if I consider A as my system, then the force acting is the rope, the tension is now considered as the external force for A. And then you have also FA, and then you have also the gravitational force of A projected in two directions, MAG cosine theta and LAG sine theta, and then N A basically. So in this case, the T is the driving force. T wants to move this upward, and then those